Welcome to BHARGAV SUBS. Now, in today's topic, let us discuss the concept regarding uniqueness theorem 2. In previous video, we discussed that uniqueness theorem 1. Okay. In uniqueness theorem 1, like what we had discussed, similarly, there also we taken a boundary region. Okay. In boundary region, like for different charges, we took like the potential is well defined in that particular boundary region. Okay. So, in this uniqueness theorem 2, this is regarding electric field. Okay, it's regarding potential, and it like potential will be uniquely determined. Like there is a one solution, one potential value for Laplace equation in uniqueness theorem 1. Okay, potential is uniquely determined. Now in this, let us discuss uniqueness theorem 2. Here we have electric field. Electric field is uniquely determined. Their potential, here electric field. Okay, so now I took a bounded region. In that bounded region, I took some conductors, right? 1, 2, 3, 1, 2, 3, so on n. I took n conductors, and in that charge was present, and also this is a charge density rho. Okay, around these conductors there is a charge density. Okay, charge density means like the charges were present. So like I took like n conductors, 0, 1, 2, 3, so on, n conductors. So for these n conductors, each one have a charge q1, q2, q3, so on, qn. So what this uniqueness theorem says about this bounded region? Okay, so the region filled with charge density, the region filled with charge density rho, and surrounded by a conducting bounded region, conducting boundaries, surrounded by conducting boundaries. The electric field is uniquely determined by total charge on the conductors. These charges there now, like total charges on the conductors determines the electric field. Okay, on this like charges present now, or you can say in another way, in a volume V. Okay, volume V. This is the volume V region surrounded by a conductors and containing charge density rho is uniquely determined on U is uniquely if Q on each conductor is given. Okay, if charges are given, then only you can able to determine the electric field. Okay, total electric field, like total electric field is uniquely determined. Like you will get a one electric field value, because if you take two electric fields also, E1, E2, okay, I can able to prove one electric field is determined here, right? Like see, if I take E1, E2, okay, then I applied Gauss law. If I applied Gauss law and a divergence theorem, okay, and divergence theorem, if I took two electric fields and I applied Gauss law, what is the formula for Gauss law? Rho means charge density by epsilon naught. Okay, gradient of E is equal to rho by epsilon naught. This is Gauss law. And applying divergence theorem, and divergence theorem means like volume integral is equal to surface integral. Volume integral is equal to surface integral. This is the divergence. So by applying this, I can able to prove E1 is equal to E2. So like where this concept was used. Okay, so it not only determines the electric field value, it also determines the potential distribution around this conductor in this bounded region. The potential distribution, first one, to find the potential distribution. Okay, potential distribution, and also we can find electric field. Electric field is uniquely determined. These both can be able to find this uniqueness theorem. For suppose if I take a conductor, okay, for suppose I took this conductor, I have plus, minus, minus, plus. These are the charges. So this type of conductors which has charge distribution, I can able to find electric field value by taking as a node charge. Okay, like this may attract, positive negative, this may attract. Means in this we have a charge distribution. Then by this theorem I can take these conductors have no charge here and here charge present. So by this I can able to find electric field. So while discussing the problems based on the uniqueness theorem, we will discuss the type of problems. I will explain detailedly in that. And also it can also helpful in finding the capacity values. Okay, capacity value in capacitors, where charge is distributed. Okay, that's charge must be present. Charge should be present. And also one more point, even though potential was not there, potential distribution not there, without potential distribution also you can able to find electric field. Without potential distribution also you can able to find the electric field uniquely, right? Yeah, like this is the uniqueness theorem 2. Uniqueness theorem 1 says potential is uniquely determined. Potential is uniquely determined by like it has Laplace equation has only one solution by substituting V. Okay, V. Here it regards to the electric field E bar or E vector. Electric field is uniquely determined when charges are given. Electric field is uniquely determined. Now let us discuss the proof. Means I will take E1 and E2. I will apply Gauss law. I will apply divergence theorem. I will apply this theorem integrating on both sides by taking the product rule. Okay, product rule. I apply the product rule to that proof. So finally I will find E1 is equal to E2. Finally I will get E1 is equal to E2. That is the proof for this. Okay, let us see the proof for this theorem. Remember these two statements, right? Yeah. So let us discuss now the proof regarding uniqueness theorem 2, right? So what I told, electric field is uniquely determined. So for that again I am going with the contradiction method. Like in uniqueness theorem 1, here what I am taking two values of electric field. One is E1 and another one is E2. So let us consider E1, E2. I took two values that satisfy the boundary conditions. Okay, I took a boundary now. I took a boundary conditions like Laplace, Poisson's, like all. Okay, like here we are taking like Maxwell equations. Okay, gradient of E is equal to, like these are the Maxwell equations, right? In electrostatic field, these are the Maxwell equations. So we will use those equations. Okay, so like I am taking E1 and E2 that satisfy the all boundary conditions. Let us assuming. Now applying for both, I will apply Gauss law. Here I applied one for E1 and here applied for E2. So gradient of E1 bar is equal to rho by epsilon naught. Okay, del of E1 bar is equal to rho by epsilon naught. Del of E2 bar is equal to rho by epsilon naught. Charge density is same because like you are taking in a certain boundary now, like charges were present in a equal distribution. So like charge density are same. So rho by epsilon naught, rho by epsilon naught. Epsilon naught, you know, permittivity of free space, 8.8 into 10 power minus 12 coulomb square per Newton meter. You already know the value. So rho by epsilon naught, rho by epsilon naught. So it lies between the conductors. Okay, the conductors are there, no? Conductors, conductor 1, conductor 2, conductor 3, like that. So between the conductors, charges are there, charges are present. There only charge distribution was there. Okay, like charge density rho was there between the conductors you are taking now. So like in the bounded region only. Okay, so like rho by epsilon naught between the conductors. Okay, again up to here. Okay, now again I am taking another Maxwell equation in integral form. Okay, it is in the differential form, like it is in the integral form. Okay, integral E1 bar dot dA bar. Okay, for the vectors. Okay, electric field vector I took in that, it is in the differential form, it is in the integral form. E1 bar dot dA bar is equal to Qi by epsilon. Okay, Qi means like some ith number. Okay, ith conductor, Qi by epsilon naught. Here Qi by epsilon, because like we didn't specify a particular conductor. So many conductors are there. Like in a particular boundary region, there are n number of conductors. Correct. So for n number of conductors, I will take like I, okay, like Q1 or Q50 or Q100, whatever it may be. I value is something in your number. So Q I by epsilon, Q I by epsilon. Okay, it up to here. Okay. Now what I am doing, so this only Q total by epsilon, Q total by epsilon, like outside the surface, like outside the surface region, we will like up to the outside, like Q total charge present in the bounded region, Q total by Qi by, like see, it is for E1 and E2, no? Okay, now I am taking EI, sorry, E1 only, E1, E2, so like Q total charge present in the bounded region, Q total by epsilon naught, Q total by epsilon naught. I am defining now a new electric field, okay, a new electric field vector E3 bar, a new electric field vector E3 bar is equal to E1 bar minus E2 bar. Same, there also we took like V3 is equal to V1 minus V2, or VD, we took there VD, like difference of V1 and V2, or V. Here we are taking E3, E1 minus E2. What is E1? Like again, I am applying del on both side, okay, here and here also. So del E1 bar minus del E2 bar, here del E3 bar. Okay, so after applying del on both side, now I am substituting del E1 bar rho by epsilon naught, del E2 bar rho by epsilon naught. I substituted. So now I got 0. Rho by epsilon naught minus rho by epsilon naught is 0. That is the first equation. Up to here clear? Now again I am going to the integral forms. Okay, integral forms. This is the differential form. I am going to the integral forms. In the integral forms, integral, like surface integral, okay, E3 bar dot dA bar, okay, for this, okay, for this both two, I am taking what is E3 I got, E3, E1 minus E2 I took. So I substituted E3, E1 minus E1 bar minus E2 bar. I am like separately integrating, like surface E1 integral, surface integral, closed integral, like it represents closed, circle represents closed, like the region was closed, okay, like no ways to charges to go to outside, right? Yeah, closed integral E3 bar dot dA bar is equal to closed integral, like I substituted E3. Now after doing all the calculation, closed integral E1 bar dot dA bar minus closed integral E2 bar dot dA bar. Now closed integral E1 bar dot dA bar is Q total by epsilon. Here also E2 bar is the Qi by epsilon, Qi by epsilon, Qi by epsilon. Now after subtracting I got 0. This is the 2. Now as it is 0, okay, closed integral as it is 0, so now like I got this as 0. Now I can define this as minus del of V3 because I got 0. Okay, like differentiation of V3 is 0, like so I can take E3 as minus del of V3. So for what value I will get 0? I got 0 here, I got 0. So like minus del V3. So for what value I have to substitute here, so I can get 0, like E3 0 now. So what value I have to substitute here to get 0? A constant value, because if you substitute any number, so you will get a value 0. So V3 is constant. Okay, if I substitute V3 is constant, like I substitute this constant value here, I will get 0. So I got V3 is a constant. In next further steps it is helpful. Okay, we define like finally V3 is constant. So I can take, if it is in an integral form, I can take V3 to outside. Okay, like differentiation, if I can take V3 outside. So in next further steps I will apply product rule. Okay, I will apply the product rule and integrating on both side. Okay, finally I will substitute these values, this one. Okay, let us see what I can substitute. So finally let us see the like E1 is equal to E2 will get or not. Okay, so let us move on to the next line. So like what I told, like I will take a product rule and integrate it. Okay, so I took a product rule. What is product rule? Del of V3 E3 bar, like V3 is a constant, E3 bar. So I am applying gradient to this. So what I will get initially, like you know, differentiation of uv dash plus vu dash, correct? Like differentiation of uv, you will get uv dash plus vu dash. Similarly, gradient of V3 E3 bar. So I will take constant, like I will differentiate, like sorry, I will apply gradient to initially E3 bar plus I will apply the different, like I will apply gradient to V3. I took E3 outside, I applied to this. Okay, initially I applied to E3 bar, later I applied to V3. Oh, applied to V3. Now gradient of E3 bar from 1. Okay, from equation 1. So from 1, gradient of E3 bar is 0. I substituted. Gradient of V3, like previously I told, gradient of V3 is E3, right? E3 into E3 is E3 square. So 0 plus E3 square is E3 square. Finally I got gradient of V3 E3 bar is equal to E3 square. Now I am integrating on both sides. Okay, integrating on both sides means like I am taking divergence theorem. So volume integral, like between the conductors there is a completely volume, right, which is filled with charges, has charge density rho, total between conductors. So I am integrating whole volume, is like whole volume for gradient. Okay, del V3 E3 bar d tau is equal to surface integral. This is the divergence theorem. Volume integral is equal to surface integral. What I will take for surface integral, dA bar, here d tau, right? So here V3 E3 bar is equal to surface integral for V3 E3 bar dA. I got here what the value, E3 square, del V3 E3 bar is E3 square. E3 square d tau is equal to, I took constant outside, V3 outside, surface integral of E3 dA bar, right? So again integral surface integral of E3 dA bar, again from equation 2, I got 0, right? So integral E3 square d tau is equal to V3 into 0. I substituted 0 here. Surface integral of E3 bar dA bar, closed surface integral. I substituted 0. Now finally I got integral, volume integral E3 square d tau is equal to 0. So E3 bar is 0. Square will go to right hand side, like it is 0. So E3 bar is 0. What is E3? Initially I defined E3 bar is the new electric field vector and it is defined as E1 minus E2. So E1 bar minus E2 bar is equal to 0. I substituted directly. So if I transfer that minus E2 bar to right hand side, I got E1 bar is equal to E2 bar. Correct. E1 bar is equal to E2 bar. So finally I got E1 bar is equal to E2 bar. So I took two vectors. I got finally the vectors are same. Like the electric field vectors are unique. If I took any number of vectors, I will get finally all the electric field vectors are equal. It means electric field vector is uniquely determined, and also potential distribution was determined. So therefore electric field is uniquely determined. Electric field is uniquely determined. This is the complete derivation. So I hope you understood. Yeah, I think if you have any doubts, comment me. I will answer to those questions. Right, I told statement and the derivation and proof for the statement I have told for the uniqueness theorem 2. Right. Yeah, thank you.